Hello, welcome to problem solving session for linear algebra. I'm Siddhi Balu Ambore from IIT Gandhinagar. Today we will discuss problems for the syllabus of week 7, that is problems related to diagonal matrix, eigenvectors, eigenvalues, and we will compute eigenvalues for given linear transformation and matrix. Okay, so we will start with the first question. Check whether the following statements are true or false. So first statement is that any two eigenvalues of a linear transformation are linearly independent. So any guesses for this, that they are asking whether given any two, not eigenvalues, eigenvectors. Yeah, any two eigenvectors of a given linear transformation are linearly independent. So what is any guess, or I hope you know what is definition of eigenvector and eigenvalues. So let me just go through it quickly. So recall that T from V to V is linear transformation. Then lambda is called an eigenvalue of T if there exists non-zero vector V in V such that this TV is equal to lambda V. Okay, so what they are asking is any two eigenvectors of a given linear transformation are linearly independent. So any guesses like what this will be? Whether this will be true or false or anything? You can write your guesses in the chat if you have any guesses. So one of the guesses that it is true that given two eigenvectors, the linear transformation is of a linear transformation, they are linearly independent. So let us see one thing. So if we have any, note that T is a linear transformation. Okay, so suppose V belongs to V is eigenvector of T corresponding to lambda. That is, we have TV is equal to lambda V and V is non-zero. Okay, so if I take AV, suppose let A belongs to R. Okay, so we are considering this vector space's linear transformation over R. So if we take A in R and A non-zero, then for any, then T of AV is what? T of AV means T of AV is A into TV because T is a linear transformation. And this is what? A into lambda V. So by properties of vector spaces, we can very well write this as lambda into AV. Okay, so T of AV is equal to lambda AV. So this imply what? That AV is eigenvector of T, right? But so V and AV are eigenvectors of T, but Clearly, if A I choose to be non-zero, then VAV is linearly independent set. So it's not true actually, because we just have, so if V is a eigenvector, then any multiple of V will again be a eigenvector. Okay, is it clear? This is not, this is, but is linearly dependent. It is linearly dependent set, because we can have this minus AV plus 1 into AV, 0. And so this is non-zero linear combination of V and AV. So that's why V and AV are linearly dependent. So this statement that any two eigenvectors of a linear transformation need not be linearly independent. Okay, so this statement is not true. Is it clear? Any doubts here? If there are doubt, please unmute, ask, or write it in the chat. Anything as you prefer. But this is clear, I hope, that it need not be linearly independent. Okay, if given two eigenvectors, they need not be linearly independent. Now, second question. So
Can you?
there, yes,
It is not clear. Can you explain that
yes,
how
sir.
that?
So what is definition of eigenvector? So there must so for any lambda v, if this happens, this is eigenvector for lambda, right? Because t of av, I am getting lambda av. So this av becomes eigenvector. So v is eigenvector, av is eigenvector. Okay, we started with the eigenvector. So we already have tv is equal to lambda v, because we started with the eigenvector v. So V is an eigenvector, AV is an eigenvector, but V and AV are not linearly independent, right? And because clearly AV is equal to A times V. So if I call this as W, then W is equal to AV. I mean, if I consider them as two different, I mean, they are different they are different vectors. I mean, is it clear? V and
Yeah,
AV are not linearly independent. They are linearly dependent because one can be written as linear combination of other, and secondly, both of them are eigenvectors. So, given any two eigenvectors, they need not be linearly independent. So that is what is asked, and I hope now it is clear, sir.
yeah, it is clear.
Okay. Now, eigenvalues, not eigenvectors. Eigenvectors corresponding to distinct eigenvalues are linearly independent. Now, what is the case? Earlier, when we chose A and AV, both were eigenvectors corresponding to same eigenvalue, which was lambda. So now they are saying that eigenvectors are such that they are corresponding to the distinct eigenvalues. So now what is the guess? Whether it will be linearly independent or not, or we can again have such vectors which are linearly dependent. Any guesses now? So they are asking for linear independence of two vectors. So let us start. So okay, it is linear, not linearly independent. Okay, let us see. Okay. So So T is given linear, or is it given? No. Okay. So let T from V to V be a linear transformation. Okay. And let V in V be an eigenvector corresponding to, let us say, lambda or A, to eigenvalue A, that is TV is AV. Okay. And also W belongs to V be an eigenvector similarly corresponding to eigenvalue B, that is we have TW is equal to BW. Okay. And B we are assuming not equal to R. So these are two different eigenvalues, different eigenvalues, and these are corresponding eigenvectors. Okay, these are any given eigenvectors. Uh, so we started with two different eigenvalues and corresponding eigenvectors, and we will check whether this V and W can possibly be linearly independent or dependent, or what what they are. Okay, so if they are linearly dependent, or let us, so we have to check for linear independence. So suppose AV plus, not AV, alpha V plus beta W is equal to 0. Okay, so and we will check whether this AB, alpha and beta are 0 or not, or what they are. Okay, so this will imply what? That T of alpha V plus beta W will be 0, because T is a linear transformation, 0 goes to 0. So we have this thing. So this will give me what? Alpha TV plus beta TW is equal to 0. And since we know what TV and TW is, it is alpha AV plus beta BW. Okay, so this imply what? V is equal to minus beta B by A W. Okay, I'm just dividing by alpha V. Okay, so this is B into minus beta by alpha A W. So just I'm separating this B because B was our eigenvalue. So this much is clear, right? What I'm doing, nothing. I'm just applying linear transformation and substituting values of TV and TW as per the chosen V's and W's. So this is what we got if we have linear combination of alpha V plus beta W is equal to 0. We get that V is some multiple of this W. So now consider this TV is equal to what? Now V has this expression. So TV will be what? This B minus beta alpha A W, right? But TV is what? TV we know here is AV, and as per this, I will get V into T of minus beta by alpha A. I'm just manipulating. I'm not doing any sort of new things here as per my need. Okay. So B into T, and this is what? B into, or let me just take this also common, minus beta by alpha A T of W, and this will be minus B beta alpha A, and TW is BW. Okay, TW is BW. So I'm substituting that. So this is what? So AV I can again write the value of this V here. This is V, and that this is what I have here. Minus B square beta by alpha A W. And if I cancel this term here and here, I will get what? A is equal to B, right? W is non-zero, and this whole thing I can cancel out, assuming they are non-zero. Then A is equal to B. Okay, if you can't see this, I'm cancelling 1B here, beta here, minus here, and alpha A here, alpha A here. And I can also remove W because W is non-zero vector. Okay, so even if I am to write like this, that it is AW is equal to BW, and W is non-zero. So this implies A is equal to B. Okay, and here we can assume that alpha and beta non-zero both, and we can then very happily cancel these betas and alpha. Then we will arrive at a contradiction that A is equal to B. So no such non-zero linear combination of V and W is possible. Is it okay? So what I did here was I started with two eigenvectors corresponding to distinct eigenvalues. And if at all there exists such linear combination of them with both the scalars non-zero, because see, both, if this is non-zero linear combination, both of them has to be non-zero, because if one is zero, then this will be only, for example, without loss of generality, alpha is zero, then beta W is zero, and W is non-zero, then beta is zero. So both alpha and beta will be zero. So if one of them non-zero, other has to be non-zero. And then I'm just following the steps as it is. I'm just applying T to it, and I'm getting some linear combination here. V is equal to something, and since alpha and betas are non-zero, I can divide by alpha here. And now I'm considering this TV. As per TV, I will get this expression. And once I have this expression, I'm just substituting value of V here, which I obtained here, and cancelled the non-zero terms. So from this, I will get AW is equal to BW, and BW was eigenvector. So I end up getting A is equal to B. Any doubts? This is just smart manipulation of given information. So earlier when we chose, so this statement is false. Sorry, this statement is true, because what we had, what we obtained is that given any two linear, two eigenvectors corresponding to distinct eigenvalues, they are always linearly independent. That's what we got. Okay, so we started with two distinct eigenvalues and corresponding eigenvectors, and they cannot have this non-zero linear combination, because if they have this linear combination, then we end up getting that A is equal to B, which is contradiction to what we assume that A is not equal to B. Any doubts? If it is not clear, please let me know. I will again explain.
In this last you have proven now, after AB equal to minus B beta by alpha A into BW. Then
This
subsequently for V is written as minus beta, that you have substituted here.
here,
Okay. No,
here.
AB instead of V, yeah, that line. Can you just, that portion alone, can you just brief?
So here I was writing AV is equal to this thing and A into V. So V has this expression anyway, which I obtained here. So I just wrote it here. So AV becomes this, and B as it is, and this B I'm multiplying, then beta square alpha. And this is non-zero, I'm assuming.
Okay, it is clear. Yeah.
Okay. Alpha and
Okay.
betas are non-zero, so I can cancel them. And that's it, I mean. They're distinct, A and B. So I started with non-equal A and B. B was not equal to A, but if this linear combination exists such that alpha beta non-zero, then I end up getting alpha is equal to A is equal to B. So this was my contradiction. So by contradiction, this statement is true because no such linear combination exists. This means. Is it clear now? Okay. So I will move to next question. Every linear transformation on an n-dimensional real vector space has at least one eigenvalue. And what is your guess? So they are asking that every given linear combination, will it always have eigenvalue? That is the question asked. Okay, so there are few guesses. So let us see. They are saying that every given linear transformation on n-dimensional vector space has at least one eigenvalue. So when I say it has at least one eigenvalue means what? That for given t from V to V, there exists lambda in R such that TV is equal to lambda V for some V non-zero, right? So this is what it means, that for given TW, there always exists lambda such that TV is lambda V for non-zero V. So eigenvector means it has to be non-zero vector. So let us take this linear transformation such that xy going to 0, -1, 1, 0, xy. So by this linear transformation, what this is xy going to minus y x, right? So if lambda is eigenvalue of this t and let v is equal to xy be, and so this is non-zero, be an eigenvector of lambda, then what I will have that t of xy is equal to lambda xy. So t of xy means what? It is minus yx as per the definition. This is equal to this lambda x means lambda x, lambda y. From this what I get? Minus y is equal to lambda x. From here I get x is equal to lambda y, right? So x is lambda y. So if I call this 1 and 2, if x is lambda y, then 1 implies minus y is equal to lambda y. So this imply what? Minus y is equal to lambda square y. So since xy is non-zero, I can assume that this y to be non-zero. Okay, then I can cancel this y and I get minus 1 is equal to lambda square. That is what lambda square is equal to minus 1. And lambda is in R. So is it possible? in real number, we are getting lambda square is equal to -1. This is not true, right? Because for any a in R, a square is always greater than equal to 0, and we got that lambda square is equal to -1. So given so this linear transformation does not have any real eigenvalue. Is it okay?
So if we change our field to complex numbers, then it would
Yes, I mean, if we are, yes, complex is okay, but we are asked for real vector space, so
yeah,
we not.
but my question is whether if we had a complex real space, then this would automatically be true, or do we have to do certain other assumptions?
No, I guess in that case it will be true. Uh, I mean, I'm not sure at this moment, but I guess it will be true because linear transformation means we can write it in forms of matrix, and matrix will have then from that matrix we can obtain the characteristic equation, and since say complex numbers is algebraically closed, it will have it will always have a root. So in that case, I guess it will have eigenvalue.
Okay.
Yeah.
But here it was not asked that whether it is a real eigenvalue. No? It can be eigenvalue can be
If we
complex
are asked
also.
the vector space is real vector space, then we will look at the eigenvalues in the set of reals only.
Okay.
Yeah. Okay, so I hope this is clear now. And so this is now fine for this, that there exists a linear transformation on a real vector space without a real eigenvalue. Okay, and this is true, right? Because we just saw above, we can use the above example for this, and we can see that this linear transformation, this T here, this does not have any eigenvalue, any real eigenvalue. Okay, and this was false, that every linear transformation, it need not have on real vector spaces, it need not have eigenvalue, real eigenvalue. Is it okay? This is clear. I mean, this question was just kind of changing the wordings of this third question, that there exists a linear transformation on a real vector space without real eigenvalue, and this is true because this this linear transformation does not have any real eigenvalue. Okay, please ask if you have any doubt. Now we'll move to this second question. Let A be a matrix we have to calculate the following. So we will be calculating few things. The first question they are asking, we need that smallest eigenvalue of A is what? So we are asked to calculate the eigenvalue of this matrix A, and we have this proposition in which is proved in the lecture, that a scalar lambda is an eigenvalue of an n cross n matrix A if and only if determinant of A minus lambda I is 0. Okay. So so we will be using this to calculate. So they are saying lambda is eigenvalue if and only if determinant of A minus lambda I is 0. So what does this mean? That we have to, if I substitute just lambda here, then it will be some polynomial kind of, it will be a polynomial, and the roots of those polynomial are precisely the eigenvalue of given matrix A. So A is given, so I just need to calculate the determinant of A minus lambda I. So A minus lambda I will be what? This 4 minus lambda 0, 0, sorry, 1, 0, 0, 0, 5 minus lambda 0, 0, 0, 0, 2 minus lambda 0, and 0, 0, 6, and 3 minus lambda, which is equal to 0. Okay, I have to calculate the determinant of this 4 cross 4 matrix, and I will calculate it with respect to first row. So we saw by, so it will be 4 minus lambda into determinant of this thing. So determinant of this is 5 minus lambda into 2 minus lambda, 3 minus lambda minus 0, and minus this, for this I have 0, 0, minus 0 plus 0, and this entire thing plus, these are only zeros here. So with respect to this, whatever I will have here, it will be 0 plus 0 plus 0, or plus or minus whatever it is. So this is simply 4 minus lambda, 5 minus lambda, this is 0, so 2 minus lambda, 3 minus lambda is equal to 0. So what values I will get? Lambda is equal to 4, 5, 2, and 3. So these are all the eigenvalues of given matrix A. Okay, so the smallest eigenvalue in that case, it will be 2. 2 is the smallest eigenvalue here. Okay, so therefore smallest eigenvalue is equal to 2 of A. Let me write of A is equal to 2. Any doubts here? I'm just using this proposition here, and I got these 4 values of lambda, and the smallest one they had asked, so A will be 2. Now second is largest eigenvalue of A, and it is 5. Okay, we have 2, 3, 4, 5. 5, fifth is the largest one, so 5 is the eigenvalue by above calculations. Is it clear? So this is how you calculate the eigenvalues. Determinant of A minus lambda I and all the roots of the polynomial are eigenvalues of given matrix A. Is it clear?
Yes, it is clear.
Yeah.
Ma'am, it can be easily find by the canonical form also.
Yes, I mean we can do that, because in that case,
Jordan canonical form, if we find the eigenvalue, then it can be easily find.
yes, that
There
is
are
true.
two blocks.
Yes, yes. I mean, there are two blocks. Then this is lower triangular, this is upper triangular, and triangular matrix. It is diagonal entries and so on. That is true. But yeah, I mean, that's what we also got here. But yeah, I mean, we can do that. The block formation and then eigenvalues of block. Yes, but I wanted to use this proposition which is taught. I mean, not everybody here knows what is Jordan canonical form and so on. Okay, so this is the standard practice. So if this can be used even when the matrix is not in the block form. Okay, this is uh, always hold. So determinant of a minus lambda I, you just calculate this polynomial, whatever you get. If you're lucky enough, you will get such kind of thing from which you can directly get eigenvalues. Otherwise, you will have to solve the given polynomial. Okay, so now third question, we'll move to next question. So they are saying that let t from r cube to r cube be such that t of x, y, z is equal to x plus y plus z, comma x plus y plus z, comma x plus y plus z. Okay, so for a and b in R, so a, b are real, and suppose the vectors v is equal to 1, a minus 1, and b is equal to not v1 is equal to this, and v2 is equal to 1b minus 1 are eigenvectors of t corresponding to a and b respectively, corresponding to the smallest and largest eigenvalue of t, not a and b. So a and b are this. These are real numbers. V1 and V2 are given in this form, and V1 is the eigenvector corresponding to the smallest eigenvalue of this t, and V2 is eigenvector corresponding to the largest eigenvalue of this t. Okay, and we have to find a and b. Okay, so since they have asked us to find, given the information with respect to smallest and largest eigen values of t, we will first calculate eigenvalues of t. So for that, we have to find obtain the matrix of linear transformation of this t. So let us start. So we will work with the standard basis. So t of 0, 0, 1 is 1, 1, 1. T of 0, 1, 0 is 1, 1, 1. And t of 0, 0, 1 is 1, 1, 1 again. So t, if I call this to be standard matrix, it will be 1, 1, 1, 1 and 1, 1, 1. Okay. And we now will calculate the eigenvalues of this matrix. Then it is determinant of t minus lambda I. So when I write this, I mean determinant of t beta beta minus lambda I. So I will get the determinant of
Ma'am, can you please explain how you got the T beta beta?
okay, so I am assuming beta is this 1 0 0 0 0 1 0 and 0 0 1. Okay, and this is linear transformation matrix of this t corresponding to this beta. Okay, so t of so what this matrix is, matrix t beta gamma is obtained using, so beta, we start with the beta, then t of beta 1, beta 2, t of beta n, t of beta n, And the vertical columns are corresponding to gamma 1, gamma 2, gamma n. So what I do, I write T beta 1. So beta is basis on the domain, gamma is basis on codomain. Then I write this, I take T beta 1 and express that in terms of gamma. Gamma means the elements of gamma 1, gamma 2, gamma 3. So I can write it in the linear combination of gamma i's and corresponding entries. So the coefficient corresponding to gamma 1, I write it in this first entry and so on. Okay, so this is matrix of this form where each entry is T beta I corresponding coefficient of gamma I. So when I write T of beta 1, so beta 1 is this 1, 0, 0. So T of 1, 0, 0 is 1, 1, 1 because of T is what? T x y z going to x plus y plus z, or x plus y comma x plus y plus z comma x plus y plus z. So this is 1 plus 0 plus 0, 1 plus 0 plus 0, 1 plus 0 plus 0. And if I am to express this in terms of these matrices, then it is just, if I call them beta 1, beta 2, beta 3, this is just beta 1 plus beta 2 plus beta 3. Okay, so 1 beta 1, 1 beta 2, 1 beta 3. So this vertical entry is corresponding to T beta 1. And T beta 1, I am expressing it again because I am going from beta 1 to beta 1. So I am expressing beta 1, the T beta 1 in again in the linear combination of beta 1 and writing corresponding coefficients. Is it okay now?
First part okay, but then again when you wrote T beta 1, whether it will be 1 plus 1 plus 1 or
It will be 1 plus 1 plus. So T, now I'm going to beta 2, right? Beta 2 is what? T of 0, 1, 0. So it is again 0 plus 1 plus 0, comma 0 plus 1 plus 0, comma 0 plus 1 plus 0, which is again 1, 1, 1, right?
okay.
Okay. So
Yeah.
I'm just evaluating these three elements and T is given here. Okay. And then these are just addition of all these three again. And just I'm getting this. So this T beta beta. And so now let us calculate this determinant of 1 minus lambda 1 1 1 1 1 minus lambda 1 1 minus lambda. Okay. So determinant of, I will do this thing. I will add all three of 1 minus lambda. I will make this like this. 3 minus lambda, 3 minus lambda, 3 minus lambda, 1, 1 minus lambda, 1, 1, 1, 1 minus lambda. So what I'm doing is R1 is equal to, sorry, C1 is equal to C1 plus C2 plus C3. So I'm just adding all the three columns and determinant still remains same in this case. Okay, so this is what determinant of, I can just now take T minus lambda common and determinant of now 1, 1, 1, 1, 1 minus lambda, 1, 1, 1, 1 minus lambda. And now I will calculate determinant with respect to first row. So it will give me 1 into 1 minus lambda, 1 minus lambda square minus 1 plus 1 into this 3 minus lambda is still there. Plus, sorry, minus 1 into 1 minus lambda. Sorry?
I think in step number 2 where you wrote C1 equals to C1 plus C2 plus C3, it is just for the first column, is it?
Yes, it is for first column. That's why I
Okay.
wrote C1 is equal to C1 plus C2 plus. Okay, because two and second and third column are anyway as it is. So I'm just adding all the three columns. And last one is plus 1 into 1 minus lambda. And this is again 3 minus lambda into this. I'm just omitting a few steps. Plus lambda, and this will give me 3 minus lambda 1 minus 2 lambda plus lambda square plus 2 lambda minus 1. So this is 3 minus lambda into lambda square. This 1 and this 2 lambdas get cancelled. So lambda has possible values 0, 0 and 3. Okay. So they are saying that this V1 is corresponding to the smallest eigenvalue, which is 0. So what I have is T of this 1 comma a comma minus 1 is equal to 0, 1 comma a comma minus 1. So this is T of 1 comma a comma minus 1 is equal to, so but what is T of a comma 1 comma minus 1? It is 1 plus a plus minus 1. So 1 plus a minus 1, 1 plus a minus 1, which is 0, 0, 0. So this get a comma a is equal to 0, 0, 0. So this imply what? A is 0. Any doubt? So a TV1 is eigenvector corresponding to 0, that is smallest eigenvalue. Is it okay? No. Similarly, I need to find, so A is 0. Now I need to find V. So now since V2 was eigenvector corresponding to largest eigenvalue. So largest eigenvalue here is 3. So V2 is eigenvector corresponding to 3, that is largest eigenvalue. Okay. So these imply what? That T of 1 comma b comma 1. So B was this, V2 was this into 3, 1 comma b comma 1. So this is 2 plus b. I'm just adding all three. 2 plus b. 2 plus b is equal to 3 comma 3b comma 1. 3 comma 3b comma 3. So this gets, so 2 plus b is equal to 3. This implies b is equal to 1. Okay. So this was the required thing which we needed. So this implies b is equal to 1. Okay, so we obtained the values of a and b which was asked. Is it any doubt here? This was completely calculation based question. Ma'am, can we take standard basis always to find smallest and largest eigenvalues? Yes, we can. So if we have eigenvalues are corresponding to the linear transformation. So doesn't matter which basis you take, eigenvalues will always be same. It won't change if we change the basis. So you can always use standard basis to calculate the eigenvalues.
Ma'am, can you explain the last eigenvalue, value of value of B?
So we want to calculate B, and B is here in V2. V2 is the eigenvalue corresponding to the V2 is an eigenvector corresponding to the largest eigenvalue. So largest eigenvalue is 3 here. So that's why I took this TV. So this is what TV2 is equal to 3V2, right? This is the definition of eigenvector. So this implies what? That T of 1 comma b comma 1 is 3 1 v1. I'm just substituting value of v2 here. So this is what? T is what? X comma y comma z going to x plus y plus z comma x plus y plus z comma x plus y plus z. So just this is x plus y plus z. 1 plus b plus 1, 2 plus b, 1 plus b plus 1, 2 plus b, 1 plus b plus 1, 2 plus b, and 3 I'm just multiplying here. 3 comma 3b comma 3. So from first here itself, and this holds for second also, that 2 plus 1 is equal to 3 into 1. So second coordinate is also satisfying. And third is equal to, so anyway 3 plus 1 is equal to 3. So third coordinate is also, so there is no contradicting value of b. So b is equal to 1 is your required value of b. Any doubts now? Is it okay, sir?
Can you just
Yeah,
tell how that?
is it okay?
Sorry, sir.
Is it okay, ma'am?
Okay. Sir, you were saying
Yeah.
something?
Yeah,
Mhm.
can you just go scroll up
Yes, sir.
in that this 3 minus lambda, from where it has come?
This I took common from here. This first row.
From the column 1.
From column 1. This is just calculation trick we use to calculate determinants. If all the 3 rows add up to same number, we just club them and take that number common, and we get one row with 1, 1, 1, 1, and we can calculate determinant with respect to that column, or in this case anyway row and column are same, so doesn't matter. Is it okay? This 3 minus lambda I took
Here
common
actually
from first.
here actually we are finding the eigenvalues, right? In this.
Yes, sir.
Okay.
One thing I would like to explain here is, or mention here is that even if you don't directly calculate this 0 and 3, you can just go on substituting values. For example, let me just quickly write it for at least a. So if I assume just lambda in R and go ahead with this, that t is of 1 comma a comma minus 1 is equal to lambda 1 comma a comma minus 1. Okay, I don't know the value of lambda. They have given that it is eigenvector, so we can assume it with respect to some lambda. So from this also I will get this, right? A comma a is equal to lambda comma a comma minus lambda. So this will give me what? A is equal to lambda. A is equal to, here it will be lambda a. A is equal to lambda a, and third I get A is equal to minus lambda. So A is equal to lambda and A is equal to minus lambda. So this gives me what? A is equal to 0, right? If A is equal to plus and minus of a number, then it has to be 0. And this second also is clear here, that 0 is equal to lambda times 0. Second equation is also satisfied. So even if we don't know the exact values of lambda, the smallest and largest value of explicitly of eigenvalue of t, we can just go ahead with the given information that lambda is just this v1 is just eigenvector corresponding to some lambda, and I go on calculating, I will still get the required result. And similarly for, let me just write it for b also, that if I take this 1 is equal to lambda 1b1, that in that case I will get what? 2 plus b 2 plus b 2 plus b is equal to lambda comma lambda b comma lambda. So this will give me what? 2 plus b is equal to lambda, 2 plus b is equal to lambda b, and 2 plus b is equal to lambda. And from this I will get b is equal to lambda minus 2. And if I substitute it here, I will get 2 plus lambda minus 2 is equal to lambda b. B is again what? Lambda minus 2. So this will give me, then again, just your calculation, lambda is equal to lambda square minus 2 lambda, and this is lambda square is equal to 3 lambda, and from here I can take lambda is equal to 3. Can just cancel lambda, assuming that lambda is non-zero, because from here I anyway got that lambda is 0. So this is largest. So is it okay? So from here I will get that lambda is either 3 or lambda is 0. Since B was corresponding to largest eigenvalue, lambda has to be 3. Since V2 is eigenvector corresponding to largest eigenvalue, and from here I will get B is equal to t minus 2, which is 1. Is it okay? I mean, are you getting what I'm trying to say here? Even if you don't know the explicit values of lambdas, that is smallest and largest eigenvalue of lambda, you can just go ahead with calculating A from given condition that it is eigenvector corresponding to some lambda, and you will still get the answer that A is 0 and B is equal to 1. Is it okay? I mean, if you don't get it, if you are not clear with this, it's okay. But this is just something I just wanted to mention. It will kind of save your time in the exam if you are appearing for exam. Okay, so if there is any doubt, please let me know. Otherwise, I will go ahead with next question. Let B be a 3 cross 3 matrix with eigenvalues 0, 1, 2. Now they are saying check whether following statements are true or not. Okay, so first statement is that the rank of B is 3. Any guesses? They are saying that rank of B is 3.
False.
Not
It's
true.
Yeah, exactly. It's not true because
Because the
we can
determinant is
choose
zero.
B
Yeah.
we can choose B to be this matrix. This matrix, because B is any matrix with 0, 1, 2 as eigenvalues. And if we know this matrix is in row echelon form, okay, first row is 0, we no need to check anything. Second row has first non-zero entry 1. Second row has first non-zero entry 2
Ma'am,
is
we,
okay, but
we
I
can
can.
directly check that, ma'am, the determinant to be is 0.
Yes, determinant. Yeah, this is also true that if any matrix has rank, so if n cross n matrix has rank n, then determinant rank is equal to n. Then determinant, if
Determinant of that matrix is not equals to 0.
determinant or determinant of that matrix is non-zero, and which is false in this case. Okay, so the rank can be 3. This is 3 cross 6 matrix with determinant 0. So determinant of B is 0. So therefore, this is false. Okay, this statement is not true. And we can also check using this that this is 3 cross 3 matrix, and we can have its row echelon form to be just 1 here. We have to multiply by 1 by 2 in the third row, and we will get this matrix in row echelon form. And from that, you can clearly see that this matrix has rank not equal to 3 at least.
It has two non-zero rows.
Yes, it has 2 non-zero rows, so it will
Therefore,
be
the
2
rank of
actually.
B is
Rank
2.
of B will be 2. Okay, now second question is the matrix B plus I is invertible. Okay, Now this B is any given matrix. Okay. Earlier we could, earlier this was the case where, I wanted to prove this statement to be false, that the rank of B is 3. I wanted to say that it is false. So I just produced one matrix where eigenvalues were 0, 1, 2, but its rank was less than 3.
It is true
So
also
I
because
got that rank of B. So I got that this statement is false. But now I'm to say that matrix B plus I is invertible. So as sir said that this is invertible, so I have to prove this. I just can't assume a matrix. For example, I can't take this above B and say that B plus I now becomes 1, 2, 3, and this matrix is invertible. That's why my matrix this B plus I is invertible always for any given matrix B with eigenvalues 0, 1, 2. Then that is false. Okay, that's now how we prove some statement to be true. Okay, so I have to prove this for any given general matrix B with eigenvalues 0, 1, 2. Is it okay?
yeah, it is okay, ma'am. It is invertible.
It is invertible, but we need to prove this. Okay.
Because we have the eigenvalues, the matrix B plus I has the 3 non-zero eigenvalues.
And how are we concluding that?
Because it is now in उसमें diagonalization form में है ना तो
वो because I assumed this B to be अभी B could be any matrix. It could be any given matrix with eigenvalue 0, 1, 2. It could be some A, B, C, D, E, F, G, H, I with eigenvalues 0, 1, 2. Okay. The given statement is for any given matrix B with eigenvalues 0, 1, 2. Can you say that this is in diagonalizable form when I add I to this?
yeah.
We can't, right? Just by adding I, we won't get it to be in diagonal form or upper
Yeah.
or lower. Okay, so let me go ahead with the proof and we will see how it could be done. Okay, so first recall that from the lectures that lambda is eigenvalue of T if and only if there exists a non-zero V in
non-zero V
null space of T minus lambda I if and only if T minus lambda I is not injective. Okay, this is something which is given. Okay, so if this B plus I is invertible, so if B plus I is not invertible, this implies that B plus I is not injective, right? Because we are in finite dimensional vector spaces now. So this is true, this holds. So this will imply what? This LB, corresponding linear transformation. This will imply what? That there exists V in V such that V belongs to null space of LB plus I. Okay, and I can just write this null space of LB plus minus 1 I, LB minus 1 I. So this will imply what? That minus 1 is eigenvalue, or let me write this. This implies LB minus, or I could have obtained this from earlier statement also, is not injective. This implies what? Minus 1 is an eigenvalue of B. But this is not true, right? This is not true because
B has
eigenvalues of B's are
0, 1, 0, 1, 2.
0, 1, 2. Okay. Is it clear? Like we just use this form, and in fact, this statement is not needed. Let me just mark this. This was not needed, but still I wrote this. But from here itself, we could have written this, that LB plus I can just write this as LB minus I, and this is not injective, so minus 1 is eigenvalue of B using this statement here. Okay. And so minus 1 becomes eigenvalue of B, but that is not true because eigenvalues of B are 0, 1, 2. Okay. Is it clear now? That therefore this statement is true. That this has to be invertible, because when we assume that this statement is that B plus I is not invertible, we arrived at the contradiction. So this is how we prove the statement. Now this, when I write for any given, so when I write this here, this is true for any matrix B with eigenvalues 0, 1, 2. B could be in any form with eigenvalues 0, 1, 2. It need not be diagonal form or upper triangular, lower triangular, or block matrix and so on. It is just any given matrix with eigenvalues 0, 1, 2. Okay, and this statement holds in general. So that's why B plus I is invertible. So I hope this is clear. If you have any doubt, please write it in the chat. I'm moving ahead with the third question, that 4 is an eigenvalue of B plus 2I. Any guesses that 4 is eigenvalue of B plus 2I? Okay, sir. And I will again use this above statement that lambda is eigenvalue if and only if. So note that if 4,
It is also true.
yes, it is true. Okay. So let 4 be an eigenvalue of B plus 2I. So these imply what? That LB plus 2I, 4 is LB plus 2I minus 4I is not injective, right? I'm just writing definition of this here, that 4 is eigenvalue of this linear transformation. So these imply what? Or I can just write B here. I hope you understand what this means. And is not injective, and this imply what? That B minus 2I is not injective. These imply what? That 2 is eigenvalue of B. But this is true, right? So I can just revert this because these were all if and only if statements. So I get that. So this is true. This holds, or let me write this holds. Therefore, I can trace back everything and I get that this also holds. So that's why this statement is true. Any doubts here? I'm just using this. Where is it? This statement here, this star. And
Ma'am, here is the injective means that that means the 1, 1.
yes, sir. 1, 1 means injective means if Tx is equal to Ty, then X is equal to Y.
Yeah, 1, 1.
Yeah. Is it clear? If you have any doubt, please write it in the chat or let me know. Okay, so I'm moving now to the fourth question. of the eigenvectors of the matrix B form a basis of R3. Any cases that eigenvectors of B will form basis of R3.
And the matrix B is the above matrix is 0, 1, 2 eigenvalues.
Yes, it is same. It is of the same question that 0, 1, 2 is eigenvalues of B, matrix B.
So we have distinct eigenvalues. That would imply we have distinct eigenvectors.
Exactly. This is what the essence of this, that we have distinct eigenvalues. So we have distinct eigenvectors, and since there are three distinct eigenvalues, we will have three distinct eigenvectors, and that's why this matrix B
We form a basis.
will form a basis of R3 because R3 has dimension 3 and we got three vectors which are linearly independent. Okay,
Yeah.
so we'll use that. I mean, if it is, shall I write the argument for this, or let me write let V0, V1, V2 be eigenvectors corresponding to V1, V2 of 0, 1, 2 respectively. Okay, then if A V0 plus B V2 plus C V2 is equal to 0, then T of A V0 plus B V1 plus C V2 is equal to 0. And this is what? A into 0 V0 plus B V1 plus 2C V2. And this will give me what? B V1 plus 2C V2 is equal to 0. But this implies B is equal to C is equal to 0 since B and C are eigenvalues. Sorry, eigenvalues. Sorry, V1 and V2 are eigenvectors corresponding to distinct eigenvalues. Okay. So from this, I will get what? That A V0 is equal to 0. But V0 non-zero as it is an eigenvector. So these imply what? A is 0. So A is equal to B is equal to C is equal to 0. So this implies that V0, V1 and V2 are linearly independent. Is it clear? I mean, whatever you all said, that since we have distinct eigenvalues, we will have distinct eigenvectors. That's what we used here.
So only under the situation that there are distinct eigen values, only then it will form the basis. Is it?
I will
My doubt is
just
that can we say in place of matrix B for any matrix, eigenvectors forms the basis of R3?
So if a matrix has, for example, if I have 5 cross 5 matrix, okay. For example, we had earlier 2 cross 2 matrix. And 2 cross 2 matrix, we saw that it did not have any eigenvalue. So it did not have any eigenvector. So in that case, eigenvector need not form basis. But if matrix is n cross n and it has n eigenvalues, I'm not saying n distinct, but it has n eigenvalues, then those corresponding to each eigenvalue, we will have a basis. eigenvectors. So corresponding to, if all the eigenvalues are there in real, then corresponding to each that eigenvalue we will, for example, if repetitive, for example, for identity matrix, 1 1 1 are 3 eigenvalues. They were not distinct, but it has 3 eigenvectors. I mean, we can take 3 distinct eigenvectors and it will form a basis. So if it has n eigenvalues, so n cross n matrix, if it has n eigenvalues, need not be distinct, then it forms a basis. Then its eigenvectors form a basis. Is it okay?
For the basis, it can be that eigenvectors are distinct. That means the eigenvalues are distinct. If no distinct, that then the matrix don't have linearly independent vectors.
Okay.
If we are taken two eigenvalues same, then the matrix then it don't have the same linearly independent vectors. All linearly independent vectors.
But corresponding to one eigenvalue, we can have, in that case, corresponding to that eigenvalue, we will have two different uh, eigenvectors. I mean, you can see that further coming in the lectures maybe, but that holds. For now, understand this. I mean, for this case, if distinct eigenvalues, then definitely distinct eigenvectors, and we will have a basis. If there are same, then there are conditions which needs to be applied, and then we can say that it forms a basis.
Ma'am, I understood what you said, but just to reassure myself, if I rephrase the statement as the eigenvector of a matrix n into n forms a basis of Rn, is it true?
It is true if there are n eigenvectors. If you understand what I mean, if there are n eigenvalues, then it will have n eigenvectors. Then we can say that. In general, it is not true, sir. Yes.
It's not true, you are telling me.
In general, it is not true. You are saying any given eigenvectors, we can form a basis. No, because we also need to choose basis eigenvectors smartly.
No, my question, I was thinking that if eigenvector exists for a matrix, those can form basis.
Yes. But
Then,
it need to have 5 eigenvectors in that case. If matrix is 5 cross 5, it must have 5 distinct eigenvectors. If it is 4 cross 4, it must have 4 eigenvectors. There could be cases where it is 5 cross 5 matrix, but only one eigenvector. In that case, it won't form a basis. If I'm making myself clear, I hope you understand this. You can think over this.
Ma'am, can we not take the three vectors in which two vectors according to the same eigenvalues here? If we take here 1, 1, 2
then it won't have
with
to form a
eigenvalues.
basis, right? For example, I can, because I told for if V is eigenvector,
Yeah.
if E is eigenvector, then alpha V is also eigenvector. We just saw this in the beginning of today's session. But when they wrote this statement, they meant that eigenvectors corresponding to distinct eigenvalues. I mean, that's what question mean here. Is it clear now? What we discussed is clear, I hope. If I take V1, V2 to be like this, eigenvectors corresponding to 0, 2, then it won't be. But since we chose them to be with respect to 0, 1, 2, this is true. Okay. Is it clear?
If we take 0, 0, 2 be the respective eigenvalues, then we have a v0 plus b into b v1 आ जाएगा ना, b v1 means
I understood, sir, and that is true. What you are saying is true, but what I wrote here is also true. That's what I'm saying here. That we have three distinct eigenvalues. I chose eigenvectors corresponding to those distinct eigenvalues. Yes, because we already understood that if we take two eigenvectors corresponding to same eigenvalues, since and multiples are also, so I hope what I wrote here is clear to everyone. If it is not clear what I wrote, then please let me know. Okay, no doubts. So I'm moving ahead now. Fifth question is that, oh, it's not fifth. Sorry. It's question 5. Let B be an eigenvalue. B be 3 cross 3 real matrix with eigenvalues 0, 3, 5 and UVW belongs to R3 respectively. B corresponding eigenvectors. We need to check the following statements. Whether they are true or false. Okay, so first statement is that there exists X in R3 such that Bx is equal to V plus W. UVW are all eigenvectors corresponding to 0, 3, 5. Okay, and if there is still doubt in this previous question, please you can raise the doubt in the discussion forum and we will try to solve those doubts. Okay, so right now I'm moving ahead with this question, and here they have given the 3 cross 3 real matrix with eigenvalues 0, 3, 5 and UVW are corresponding eigenvectors. So U is corresponding to 0, V is corresponding to 3 and W is corresponding to 5, and they are saying that there exists X in R3 such that Bx is equal to V plus W. And what is your guess whether this statement is true or not? Can we produce a X such that Bx is equal to V plus W, or such X does not exist?
So when we say V plus W, that would imply that it is 3V plus 5W.
It is 3V plus 5W. What I mean, I'm not. So they are asking
So
X.
sorry,
Yeah.
what I mean is that this
Mm-hmm.
3 is lambda eigenvalue and V is the eigenvector. So
Yes. So
that
what
would be
we have called now
lambda.
is
So
B.
lambda V would be 3V and the other one would be 5W.
So BV is equal to 3V and BW is equal to 5W. I think this is what you mean.
Yeah.
Yeah. This is what I have. So can we have X such that BX? So they are asking whether such that I can have this. X I need to find X. Or if exist. Any cases? So sir said that this is true, and which indeed is true, because we can choose this X is equal to 1 by 3 plus 1 by 5 W. Okay. And when I apply B to this X, then this is B of 1 by 3V plus 1 by 5W. So this is 1 by 3 B of V plus 1 by 5 B of W and B of W. And this is V plus W because B of V is 1 by 3V and BW is 5W. So we got this X. So this statement is true. Okay, because we just obtained this V such that this holds. Any doubts here? This X works. If not, then I'm moving to second question, that dimension of null space of V is 0. So they're asking dimension of null space of B is 0. It means when I say
So you
dimension of
will
null
have a
space is
full
0.
rank matrix.
Yes, it must be a full rank matrix, and there, I mean, what it means that nullity is 0, means only it is injective map. That's what they are asking. And this is clearly not true, right? Because we have U in R3 such that, yes, it is false, such that BU is 0, right? So U is non-zero and U belongs to null space of B. So therefore dimension will be at least 1, right? I mean dimension of null space will be non-zero. It will be at least greater than equal to 1. Okay, because we have non-zero element belonging there. Is it okay? Now next question is, there exists, so this is false as also suggested by so in the now the next question is, there exists infinitely many X in R3 such that Bx is equal to V plus W.
Sorry, if we can go back to the last problem, we
This one,
got
okay,
yeah,
yes.
we got Bu is equal to 0 because the eigenvalue in that case is 0, right?
Yes, yes.
Okay, okay.
Yes.
And we
Bu
can't
is 0.
have
This
such vector. Okay, where it is not equal to 0. Okay, got it.
It's clear, right? This is 0U and this which is 0. Okay. Now I hope it is more clear than the previous statement. Now they are asking that there are infinitely many X in R3 such that Bx is equal to V plus W. Okay, so guesses are that it is false, and let us see. Note that if I take X to be V plus W, then we already saw V plus W to be X is equal to 1 by 3V plus 1 by 5W. Then we already saw that Bx is V plus W, right? But now if I take X to be U plus 1 by 3V plus 1 by 5W, in that case, what is Bx? It is Bu plus 1 by 3 BV plus 1 by 5 BW, and this is 0 plus V plus W, which is V plus W, right? And instead of just taking U here, I can very well take alpha u, and this alpha 0 will still give me with alpha in R. With alpha in R. This still holds, right? That if I take x is equal to alpha u plus 1 by 3v plus 1 by 5w, then bx in that case is this v plus w. So therefore, I can vary alpha and I will get infinitely many x's such that bx is equal to 0. Sorry, bx is equal to u, v plus w. Any doubts here? This statement is true actually. Okay, and let me just... Okay. Any doubts here that this alpha u I'm just taking because u is such that bu is 0. So, and u is non-zero. So I can take multiples and still v alpha u will be still 0 because it will be alpha bu, but bu is 0. So alpha 0, which is 0. If there are any doubts, please let me know.
Ma'am, can we not solve this by taking A, B, C, alpha, beta, gamma in general?
In general, if we go, then you will just have to find what will be the coefficients of this v and w. So if you can find that, then that's okay. But the question was, does there exist? So we produced this x such that there are infinitely, or x alpha, let me write here, such that this x alpha is giving me b x alpha is u v plus w. So that's why this much is enough to show that there are infinitely many x. We can, if you want, you can go ahead and find the coefficients of v, w, and u such that in that case also you will get infinitely many UVWs. That's not a problem. But this much is enough to prove that there are infinitely many x. Is it okay? I mean, sir, what you said, you can obtain the coefficients of v and w in general and solve this, but this holds. We just had to show that there are infinitely many such x's, and we showed that this x actually give the required set. There could be more than this, but at least these many are there, which gives us that bx is v plus w, and this is infinite set. Infinite
Ma'am, I think
has
that it is false.
alpha belongs to R.
Not many x belongs to R cube such that bx equals to v plus w. If we take here x alpha equals to alpha u plus beta v plus gamma w, and bx alpha bx equals to ये ले हम alpha bu plus beta bv plus gamma bw, then we take here alpha 0, that means it will be 0, and here is beta 3 beta v plus 5 gamma w equals to v plus w. Then we can only find the values of beta and gamma 1 by 3 and 1 by 5.
That is okay, but alpha still varies, right? You can take alpha to be anything.
नहीं तो what alpha, that means
Alpha you, okay, so if I take alpha to be 1, so x is u plus 1 by 3v plus 1 by 5w. Okay, now bx is what? It will be v plus w. Okay,
yeah.
Let me call this x1. I take x2 to be 2u plus 1 by 3v plus 1 by 5w. Then bx2 is what? Still, it will be 2bu plus this thing is anyway will give me v plus w. But 2bu is what? 2 into 0 plus v plus w. And I am getting 0 plus v plus w, which is v plus w. And I give me any alpha in R, x alpha into u, for any alpha. Give me any alpha. This holds, right? Alpha u plus 1 by 3v plus 1 by 5w. This will be what? When I take bx alpha, this is just notation. This is bxu plus this, we know that this is v plus w, but this is alpha bu plus v plus w, which is 0 plus v plus w, which is v plus w. So we can vary. So this beta and gamma, as you said, beta and gammas are 1 by 3 and 1 by 5. That is okay. That's not a problem. But I can vary alpha. And as I vary alpha, I get infinitely many x's. Is it okay? Beta and gamma are fixed. They are fixed. Okay, but this varies
This
over R.
alpha can take any values.
Yes, so that's why it is infinitely many. Is it okay now, sir?
Yeah, okay.
Yeah. Okay, so this statement is true.
Is it because we have a zero eigenvalue? That is the reason.
Yes. Because if we do not have any zero eigenvalue, in that case, this will be full rank matrix, and it will be then isomorphism, and this will be then injective map. So we cannot have such expression where, and in fact, it is 1-to-1 map. Each element has one and one. I mean, each element has one pre-image kind of stuff.
Okay.
Is it okay? It will be full rank matrix, and then it will be isomorphism. So it will be injective. That in that case, for no v plus w, we can have infinitely many x. So, I mean, is it okay? I mean,
Yeah,
I'm
yeah.
making myself clear. Okay, it will be full rank matrix, and it will be in fact isomorphism. So this does not hold in that case.
And
Yes,
I think
you are
that is
right.
why you said that they need not be unique. I don't want to open that discussion again, but when you said the eigenvalues need not be uh, distinct, but it needs not be zero. That's the
Yes,
criteria. Okay.
yes.
Okay.
Okay, and just since you said about the zero eigenvalues, zero transformation is also linear transformation with all the eigenvalues zero, but still we have three distinct eigenvectors corresponding that single zero eigenvalue. If I'm making myself clear, just for you to think over it.
Okay.
Okay. So I'm going to this next four. That, yeah. Let me check that. There exist x in R3 such that bx is equal to u. And any guesses here that whether this will be true? Can we produce such x such that bx is u?
False होना चाहिए मैम.
Yes, it will be false. Okay, and we will see how.
Because B has the zero eigenvalue.
B has zero eigenvalue, that is okay, but let us see how this is not true. So first is, we all agree that rank of B is 2, right?
Yeah.
0, 3, 5. So rank of B is 2. Everybody is okay with that, right? Anybody has doubt that rank of the B is 2?
No ma'am.
Okay. If you have any doubt with this, that rank of B is 2, please let me know in the chat. But for now, because B is what? This will be similar to some diagonal 0. I will explain this like how this is in next question. So rank of this is invertible. This is invertible. So rank of B in that case will be rank of this diagonal D, suppose. Then this will be 2. And this is from the previous lecture proposition, which I said that if I have invertible matrices and if I multiply invertible matrix by any matrix, then rank of original matrix does not change. So if a like rank of A is some R, then rank of QA will be also R, QP, PQ also R, and PAQ will also be R. Given that P and Q are invertible matrix of required rank. Okay, so this was from the previous lecture, and this is because B is similar to this diagonal. This is from current lecture, and we will discuss this in few minutes. But for now, rank of B is 2. This is, I hope, clear. So since V and W belongs to so note that V belongs to range of LB and W also belongs to range of LB. Because I can take, we can have this T of 1 by 3 V is equal to V and T of 1 by 5 W is W. So these two elements are there in range space, and I mean, I'm just giving explanation why the rank is 2. I mean, not the, I'm already assuming that rank is 2, and I'm just producing the basis now that V and dimension of RLB is 2 and V and W are linearly independent. Therefore, V and W is, span of V and W is range of LB. Is it okay? I just wanted a basis of range. Okay, so now if Bx is equal to U for some x in R3, then U belongs to R of LB, right? If Bx is some U, if for some x Bx is U, then this U belongs to range space. So this will imply what? U is equal to some alpha V plus beta W, right? Because we just proved that RLB is formed by V and W, or RLB, V and W forms basis for RLB, that is range of LB. And this is not true, right? We can give the same argument which we gave in the previous example for 0, 1, 2. That these three will be linearly independent always. We again apply B on this, and we will get that this 0 is equal to this V, some alpha, some gamma V plus delta W, and those will be again 0 because linear combination V and W are eigenvectors corresponding to distinct eigenvalues, and again I will get that everything is 0. Is it okay? I will get that if I apply B here, Bu is equal to B alpha V plus beta W. Let me write. 0 is equal to 3 alpha V plus 5 beta W. This will imply alpha is equal to beta is equal to 0 since V and W are linearly independent, since eigenvectors corresponding to distinct eigenvalues. So this implies that U is 0, but which is not true, as VU, not true, as U is eigenvector vector of B. So therefore, no such x exist. No, so Bx is equal to U does not hold. Is it understandable? Please let me know if anything is. So what I did was I used the fact that rank of B is 2. I produced a basis using two eigenvalues which were already given, and the corresponding eigenvectors gave me basis because dimension of range space was 2 and I have two distinct linearly independent two linearly independent vectors, so that will form a basis for this RLB. And if Bx is U for some x in RQ, then U will be in a range, right? That is the definition of range. So RLB means what? All those, I don't want to use, so let me write x, not x. All y in R3 such that y is equal to bz for some z in R3. This is the definition of RLB. And if that is the case, if U is in RLB, so using the span, this is what it means. And from BU, I get U to be 0, but that is not true because U was our eigenvector corresponding to 0. So that's why Bx is equal to 0 does not hold. Is it okay? If there are any doubts, please let me know. If not, I will move to next question. If you still have any doubts, please think over it and ask the doubts in the chat if possible. Okay, so meanwhile I'm going ahead with next question. So let T be a linear operator on finite dimensional vector space V and lambda B an eigenvalue of T. With an eigenvector V in V. So we need to check the following statements are true or false. First, they are saying that T is not invertible if and only if 0 is an eigenvalue of T. And this we already discussed earlier, right? We can use the same result which states that lambda is eigenvalue if and only if of T, if and only if T minus lambda I is not injective, if and only if there exists V in non-zero V in null space of T minus lambda I. Okay, so we can just use this because if 0 is eigenvalue of T, then this is from above statement if and only if T minus 0I, which is anyway T, is not injective. This implies what? T is not injective means T is not invertible, right? This will hold if and only if because we are in finite dimensional vector space. Okay, so since we are in finite dimensional vector spaces, this holds. And T is again from same vector space to same vector space. So therefore T is not injective, therefore it is not invertible. And if it is not invertible, it will not be injective. I hope this is clear. Since, let me write here, T is from V to V and V is finite dimensional. Any doubts here? I'm just using this statement above. If you have any doubt, please let me know. Otherwise, I will move ahead with the next question. That T is an if T is an invertible linear transformation, then lambda inverse is an eigen value of T inverse. And any cases? Okay, so this is true. As guessed, this is true. And we will just use this fact that T is invertible. So T inverse TV is equal to identity, right? Oops, T is equal T inverse is identity. So since V is a vector eigenvector given corresponding to, since given that TV is equal to lambda V, we can have T inverse TV is equal to V, right? First of all, it is V. We considered, let me, then T inverse TV is lambda V is equal to V. So which is what lambda of T inverse V. Since T inverse is linear transformation, so T inverse V is 1 by lambda V. Lambda is some eigenvector. So since T is invertible linear transformation, note that lambda is non-zero by previous statement. Okay, we have this, that T is not invertible if and only if 0 is eigenvalue. So T is invertible given, so lambda has to be non-zero. So I can take 1. So this implies that 1 by lambda is eigenvalue of T inverse. Is it okay? This was quite clear using this condition. I am then now moving to next question, that if C belongs to R, then C lambda is eigenvalue of CT. And this is, any guesses whether this holds? This will again be true. Okay, we will use the same trick, that CT V is what? C into TV, right? So CT into V is C into, since V is eigenvector, so let V be eigenvector let me write in shorthand. Corresponding to lambda. So this will imply what? CV is equal to lambda V. So then this is lambda C lambda into V. So CT is C lambda V. So this implies what? That C lambda is eigenvalue of CT. It's clear. It's clear, right? This is true. Just I'm applying the definition that V is eigenvector corresponding to lambda, and then CTV is CTV by definition. So this is the definition, right? CTV means C into TV. So C lambda V and C lambda V, I'm just taking common. And CT will have this V is going to V here, and so C lambda then becomes eigenvalue of CT. Then the fourth one, that for n belongs to n, the lambda n is an eigenvalue of the linear transformation t power n. So they are asking that whether lambda n is the eigenvector of t power n. So t power n is what? T composed with t n times. Okay, so Tn of V is Tn minus 1 of Tv, and so on. Any doubts here in the definition of T power n? This is composition n times. And they're saying that lambda n is eigenvalue of T power n for n in n. So start that let V be an eigenvalue of T corresponding to eigenvector corresponding to eigenvalue lambda. Then T of V is lambda V, right? But if I take T square V, then it is what? T of TV, and it is T of lambda V. Then by definition, this is lambda into TV, and which is lambda into lambda V, and this is lambda square V. So from this, what I got, that T square V is lambda square V. Right. And I can just continue this. Let me just write for 3. It will be T square TV, which is T square lambda V, which is lambda into T square V. So which is lambda into T square V was lambda square V. So this is lambda cube V. So we just got that T cube V is equal to lambda cube V. So we can just apply induction and assume that it is true for k many n's. N is equal to k. Then T power, or it is true for n minus 1. Then T power nv will be what? T power n minus 1 into tv. Right? Suppose or let me write induction. So this is what? T power n minus 1 lambda v lambda T power n minus 1 v lambda into lambda n minus 1 because of induction hypothesis, and this is v. Is it okay? So this is true that lambda n is eigenvalue of T power n. Any doubts here? Oh, and this is last for identity matrix I, lambda plus 1 is an eigenvalue of t plus I. When I write this t plus I identity transformation, or let me write identity map I, t plus lambda plus 1 is eigenvalue of t plus I. Okay, so again we will start with this, that let V be an eigenvalue of t with respect to lambda. Then t plus 1 I of V is what? T of V plus I of V. Okay, then t plus I V will be t of V is lambda V and IV is just V, and which is what? This. So what I got, that t plus IV is equal to lambda plus 1 V. Okay, so there's imply what, that lambda plus 1 is eigenvalue of t plus I. And using this, one can clearly state this, that if Pt is this, t power a1 an t power n, so on up to a1 t power, t plus a naught I is linear transformation, then p lambda. When I write p lambda, so if I take this p polynomial, this p polynomial, then when I evaluate that p at lambda, this is eigenvalue of p of t. And this is quite easy to see, right? Because pt of v is what? It is an t power n plus so on up to a naught I v. And this is an t n v plus up to a naught iv, and this is an t power nv. We using the previous information, everything, I get that it is lambda power nv plus a naught v. So this is what? an lambda power n plus an minus 1 lambda power n minus 1, so on up to a naught v. So this is what? P of lambda v, right? Because that was my polynomial. So if you are asked question for if you have information about lambda of a, you need not have to. So if somebody tell you that lambda is eigenvalue of some matrix A, then for this polynomial x square plus 3a plus 5i, eigenvalue will be just lambda square plus 3 lambda plus 5. This is what it says. Is it clear? Any doubts here? So you can always use this to calculate eigenvalues if asked in the question for any given polynomial corresponding to A. But note that all these T's are same. So we are only talking about identity and composition of T. Okay, if there are two distinct, so if T and S are two distinct or two not equal linear transformation, then this need not hold, that S plus T has eigenvalue lambda, then if S has eigenvalue lambda, T has eigenvalue lambda 2, lambda 1 and lambda 2, then S plus T need not have eigenvalue lambda 1 plus lambda 2. Okay, please understand this. Okay, this is not in general true, but since we are working with compositions and so on, this holds for same matrix and its power. And when I say power, I mean composing it k many times. Is there any doubt?
This last statement, can you just repeat? That is s plus t minus lambda 1 plus lambda.
This one?
Yeah, the last statement you have written.
Oh, so I'm not saying this s plus t. So if s is a linear transformation, okay, let me write this properly. If s is linear, s and t linear transformation, s and t are linear transformation, okay, and lambda 1 and lambda 2 are eigenvalues of s and t, then respectively, then lambda 1 plus lambda 2 need not be an eigenvalue of s plus t. That's what I'm saying. You can cook up examples for this and you will have this. So note that since we had v here and v was this eigenvalue of t, and when we were doing all this shuffling and manipulation or addition, subtraction, and all the good things about linear property of t, note that here we had t, and here also when we were evaluating this, it was same t working here. So that's why this was holding. But in general, this is not true, because when I say lambda 1 here and I say lambda 2 here, this lambda 1 will be corresponding to some v and this lambda 2 will be corresponding to some w, and they need not hold. I mean, I hope what I'm saying is understandable. You can think about this. If not, then we will discuss this in next session. But right now, any doubts in whatever we solved till now? Any doubts, please let me know.
I have a doubt regarding an assignment question from week 6.
Okay. Could you please let me know the assignment question? I mean,
So it's just a linear transformation from R3 to P2 of R with ordered basis alpha and alpha dash for R3 and beta
so
and
T
beta
is
dash
from R3 to
P2 of R.
okay, P2R. Okay.
And ordered basis for R3 are alpha and alpha dash.
Okay, alpha alpha dash.
And ordered basis for P2 of R is beta and beta dash.
Okay.
So we have to find coordinate matrix where T alpha beta is equal to A.
P alpha what?
T alpha beta is equal to A.
A.
Yeah. And T alpha dash beta dash is equal to B.
Okay.
So I have a question because I was considering, say, alpha is standard basis and beta for R3 and beta is standard basis for
So
polynomial.
expression of alpha beta, I mean, alpha betas are not explicitly given to you, is it?
No, they are not
Okay.
given. So I just trying to find out what the matrix A would look like. So I just want your help. If I consider alpha as standard basis and beta as standard basis for polynomial, then how do we calculate T alpha beta?
First of all, it depends. Okay, so T alpha beta. So you want to know how T alpha beta is calculated.
No, I was
Is that your?
stuck in the calculation where I considered alpha equals to the standard basis for R3 and beta is equal to standard basis for P2 of R.
Okay.
So how do we calculate T alpha beta?
So T alpha beta means, so if alpha will be some, since we are in R3, it will be some alpha 1, alpha 2, alpha 3, right?
No, I took standard basis.
Okay, so let us call me E1, E2, E3.
Yeah.
Okay. And here my beta will be 1x x square.
Yeah.
Okay. And then I'm just writing here that T of beta to, alpha to beta means first what I need to do, I need to
T of
calculate T of
E1.
E1,
Yeah.
T of E2, then it will be some polynomial in P2R. Then I will express that in terms of this some x plus x square
So everything was
P2.
coming as 1. So I was getting confused there.
Yeah,
So
so that is okay. I mean, if that's how the linear transformation is given, everything is one, that's not a problem. I mean, here in earlier first, I think first or second question, let me show you where we did that. Oops, not here. There, yeah, here also we got everything to be 1, 1, 1, right? That's not a problem. I mean, we can have a linear transformation as the way we want, and this could
if you
maybe.
can, sorry, go down, sorry,
Mm-hmm.
to the example which you were discussing.
Okay.
So the assignment question. Yeah.
Mm-hmm. Okay. By the way, what is asked based on this information?
So can we produce such a matrix? A and B.
Yeah, I mean, we can produce such matrices, right? We can always find a linear
So sorry,
transformation.
the question is, does there exist a linear transformation from R3 to P2 of R? The answer is no, but I'm stuck in this calculation itself. I was
This
not
is
able to attempt this
question
question.
6 of assignment. Let me
Question
just check.
7,
Question 7 of assignment,
week 6, last
week
week's.
6. Okay, last week. Let me check. So A and B are already given. That's what you are saying.
No, nothing is, this is what is given.
Okay.
So what is given is there are ordered basis alpha and alpha dash beta and beta dash.
Mm-hmm.
And if we produce T alpha beta equals to A and T alpha dash beta dash equals to B, does the linear transformation exist? So that's the question.
Okay, let me see the question. Question 7. Okay. Okay, I understood why it is. Okay, so why answer is no is I will give you. So A and B are what is given in fifth and sixth question. Okay, so A and B are these, like compute the rank of following matrix. So A and B are given here actually. So A and B mentioned in this question 7 are actually A and B from question 5 and 6. Okay, and then they are saying that does there exist one linear transformation which is which is giving me both the matrices, and that will not be true, because if that is the case, if T alpha beta is such that it is A, then rank of it is 2, right? Rank of A is 2. Then rank of T becomes 2, but B here has rank 3. So in that case, rank of T becomes 3. So we can't have a linear transformation with rank both 2 and 3. It has to be one of them. Okay, even Sania also asked this question today earlier, that ma'am, can we take standard basis always to find smallest largest eigenvalue? So when and if you remember, I said that take any basis of your choice and rank will always remain same and eigenvalues also will remain the same. So that's why this was false, because A and B were already given actually.
Oh, okay. So I missed that part. But anyways, when I was trying to calculate, so the first one is E1 is 100. So when you when you compute T of E1, the first column would be 1, 0, 0. Is that correct or am I wrong? And the second column again is 1, 0, 0. So I just wanted to confirm that. In the solution, it is not clear. Please tell
Solution,
me.
there is no solution. I mean, we don't have any explicit example of T for this because such T does not exist
No,
actually.
if I work with standard basis, what I'm trying to say is, if I calculate T of E1,
So give me T and I will explain you. Give me T. T is R3 to P to R, that is okay. But what is T of one XYZ, where it is going?
okay,
Where is it going?
yeah, I had
We need to,
assumed that also.
yeah.
Mm.
It is going
So
to where?
I say I considered ABC. It's going to AX square plus BX plus C
Okay, A, B, C going to AX square plus BX
plus C.
plus C. So since I'm writing this, so this is what ordered basis. When I
Yeah,
write, so as per my, so 1 0 standard basis, as you are saying, this is going to 0, this is going to 1 plus 0x plus 0x square. Sorry, T of 0 1 0 is going to 0 plus 1x plus 1x square, sorry, 0x square, and T of 0 0 1 is going to 0 plus 0x plus 0x square. Then,
1x square.
yeah, sorry, thank you. Then T, this is what? This was alpha beta.
Yeah, alpha beta.
Alpha beta. Then T alpha beta is vertically you need to write. So these are corresponding to beta 1, beta 2, sorry, alpha 1, alpha 2, alpha 3, and corresponding to this is beta 1, beta 2, beta 3. So alpha is corresponding to alpha, coefficient of beta for alpha 1, coefficient of beta 1 is 1, coefficient of beta 2 is 0, coefficient of beta 3 is 0. Second one it is 0 1 0, third one it is 0 0 1. This will be the matrix.
So what mistake I am making is the matrix the transformation 2, that is 0 1 0. I'm writing as 1 dot 1 plus 0
Oops,
dot
oops,
x plus
sorry,
0
sorry,
dot x
sorry.
square.
As per your linear transformation, this is not 0 actually. This is 0 plus ax square, 1x square. This is 0 is fine. And this is 1 plus 0. So this will be like this. Because a is 1 here and it is going to 1x square. A is going to ax square. 1 is
Okay,
going to 1x square.
okay, I got
So
my
now,
mistake. Yeah, that's fine.
yeah,
So
okay.
I was
So this is
considering because
actually like this.
so what
C
my mistake
plus.
was, I was considering 1 to go to C. So that's, I think that's the issue. In every metric, in every transformation, I was considering 1 to going to C instead of 1 going to A, 1 going to B, and 1 going to C in 3 steps. Okay, got it. Thanks.
Okay, great. Okay, any further any doubts now? Apart from this, okay. If you have any doubt, please write it in the discussion forum or the Google group which we have, and we will try to solve those. Okay. So if there are no further questions, we will end the session for today here, and we'll meet next week on Saturday at 3 p.m. Thank you.
Thank you.